Okay.
Go ahead.
Yeah, so the rule is that if there is a question, please interrupt me. And so I'm writing some notes that I'll share after my talk on like the key things that I'll say throughout the talk. I'll try to put as many problems as possible while I'll speak. And please, yes, after the talk, send me an email if you have any input, if you have any questions, so I can spend more time on that part, answer that in the next lectures. So, okay, so what is applied algebra and geometry in the infinite setting? The main object of this course are polynomial rings in infinitely many variables. And in order to make and objects that live in these polynomial rings, and in order to have some rules on or some control over objects in these settings, we use group actions. And the motivation why we do that is because we want to figure out. So the objects here are extremely large, so we want to know or understand some stabilization or finiteness or asymptotic phenomena that happen. And when I said objects in these polynomial rings, they can be ideals, varieties, algebras, modules, and we can go to combinatorics with constant polytopes. Or Carlos spoke about I'm assuming about statistical models, so you can also translate all these into a statistical setting or other applied versions. And yeah, so this is an area that has had quite development in the past, let's say, 20 years. And not only in algebra, in tensors, I mentioned here topology, more recently also in combinatorics, and but always it has had like the main like the reason why a lot of these developments happened kind of got motivated by work on algebraic statistics. Throughout these courses, we will focus on mostly on the first and the last one here, and I'll say a few words on the rest when I can. As I said, I'm gonna I will share some typed notes, but throughout this talk now, we will just write together. So not everything that I'll say is written in the notes, just some key points. So then, yeah, and the references will be there and everything. Okay, so in lecture 1, we will kind of get introduced to this world. And as I mentioned, the objects, yeah, so are these polynomial rings in infinitely many variables. So how do they look like? So, okay, so, yes. Okay. In infinitely many variables. So, okay, give me 1 second. So some examples. So the word says infinitely many variables. So some examples are like something like I'm gonna work with over real numbers, but everything can be done over any field or any closed field or with characteristic 0 or not. Then so yeah, so if we have x1, x2, x3, so and we continue this way. So for short, I'm gonna call this with r of xn. Or we can have in a more general setting x of c times n. When I write this, what I will mean is this r of xij, where I is from 1 to c and j is in n. And we can go even more general. We r of x let's say C times, I'll call n to the k, where this will be R of, now I will say X ij, where I is again from 1 to C, but J is a tuple that lives in this n to the k. So all these are examples of polynomial rings in infinitely many variables that I'll mention throughout the talk. And now the main challenge of working over these polynomial rings is that they are not Noetherians. Okay, so all these rings are not Noetherian. And what does this mean? So this means that their ideals are not guaranteed to have a generating set of finite size. Okay, so one example. Let's take just a simple example. Let's take the ideal, the maximal ideal. So generated by x1, x2, and so on in this polynomial ring R of xn. So I claim, so how many elements are here in the generating set? So we see here there are infinitely many elements, but there is no finite set of generators, finite set, sorry, of polynomials that can generate this ideal. I claim that is no finite set of polynomials that generates the ideal. And I leave this as also as kind of a question to work. Why? Okay, so you can assume that you have a finite set of polynomials, sorry, that generates everything. Then if it is finite, then probably there is a maximum index that you see there, and you can work with that. That like the variables with index larger do not live in the ideal generated by these finitely many polynomials. Okay. So we have this polynomial rings in infinite setting, and we said, okay, there are these situations when we don't have finiteness. So what do we do? So we ask help from group actions. So more specifically in this talk, we will focus on the permutation group, the group of symmetries. Okay. Symmetry. Okay, so so the idea is that, so let's denote by Sn the permutation or symmetry group on the set n, which is 1, 2 through n. And with this, let's also denote with S infinity to be the union of this Sn or n in n. So, and then define the group action. We have Sn can act on R. So let me, before I do that, let's just let's call for a moment Rn will be R of x1, in this case through xn, and R will be the big one, so it's going to be R of x1, x2, so on. And so we have two types of group actions here. So we have Sn acts on Rn itself. So in the form that if I take permutation sigma here, and if I take a variable xi, this will get mapped to x of sigma of I. Okay, so it will permute only the indices, and this extends to S infinity acting on R, such that similarly sigma xi gets mapped to x of sigma. Okay, let me know if you have questions. And now with kind of this, so back to our example. So with this setting, for instance, our maximal ideal x1, x2, and so on.
Excuse me. Yeah. This action is well defined.
Yes, yes, that's a good question, and the answer is yes. And I'll say a few words more. Give me, where do I? Okay, yeah. So it is well defined. So we are defining it on the indices, and then we extend to all the polynomials by applying the same thing. Just the permutation always acts on the indices of the polynomial. Yeah. But it can be, yeah, it can be defined only on the variables, and it extends like linearly and multiplicating, like, yeah.
I mean, May sigma belongs to S2, and the index I is, for example, 3. And what does this mean?
But so yeah, so so Sn acts on Rn right now. So in at this moment, this is all fine because Rn will have indices at most n, and Sn will permute 1 through n. And when we are here, then here may be more like this accepts all the variables, and this permutes all the variables, so we never leave the space, like we are always there. So if you have Sn like S3, so that was your question, you may have S3 here and R2 here.
I think you need to include that in union part of in order to define S infinity.
Yeah.
Probably S infinity is creating the confusion. Yeah, yeah. Now it is okay. Probably.
But I mean, when sigma is in S2, this is, for example, a permutation of on two variables, okay? I mean,
No, it's not of the variable. So sigma. Oh yeah, you can think of the variables. Okay, yeah.
okay. For example, sigma is the permutation like 1, 2, okay? And then you apply this on xi when I can be, for example, 4. How do you apply 1, 2 or on x4?
So I think your question is in this part, because here you don't have like x if you are n equal to 2.
Let me add here, because S1 is a subset, we can consider S1 is a subset in S2, and S2 is a subset in S3.
I was gonna,
So,
yeah.
Directly.
I was
in this way
yeah,
we can
thank you.
make
I was
that.
gonna say that
Yeah.
S2 we can take that permutation permutation sigma in S2, and we can extend it to a sigma in S infinity in general by just like everything else that is not 1 or 2, it's identity.
Now clear, thank you.
Thank you. Thank you also whoever helped me with the answer. Okay. So yeah, so there is an embedding of like S1 is embedded in S2, embedded and so on, in a sense. The same as there is an embedding of R1 embedded, this is exactly inclusion in R2, Rn, and so on. And maybe that makes it more clear. And so S1 acts on R1, S2 on R2, and so on, but there is also the embedding. Okay. And then so we go back to our example. So in this case, we can write, so we had this x1, x2, and so on that had infinitely many generators. We can write it as S infinity of x1. And in this case, we say that our ideal, if I call this with I is finite, has finitely many orbits, so is finitely generated up to S infinity. Okay, so kind of this gives us a way to handle infinity. We have finitely many orbits. And so I had a professor in grad school that asked this question to us in algebra that said, how do you email an ideal? And the answer was you send the generators. When you have ideal with infinitely many generators, you cannot send them via email, but you can send this one generator x1, and you can also send the group action, and then you send all the ideal. So you can. Okay, so so let's now look at another slightly more involved example. Okay, so consider now, so let's Rn to be the R that we called x2 times n. So this has just the variables x11, x21, x1 2, x22, x13, x23, and so on. And so now consider, so let's, for simplicity, I will call x2 times n. This will be the matrix. Or let me just write it how it is. So we have x 2 times n be the matrix of variables x. We write with the matrix of variables x11, x21, x12, x22, x13, x23, and so on. So this is a 2 by n matrix. And so let's I be generated by all 2 by 2 minors of x2 by n. And okay, so what would this be? So will be x11, x22 minus x12, x21, x11, x23 minus x21, x13, and so on. So there are how many generators? So there are, how many generators are there? We just need to choose 2 columns, and they fully determine the minor. So there are, it's funny, n choose 2 is infinity. So there are many generators, infinitely many generators. And in fact, this makes a Grobner basis. So a lot, let's say, a lot of generators. However, we can, again, as before, apply a group action. So take S infinity, act on this, our polynomial ring. Oh, I call them with n here. With n, I mean when okay, every time I put a lowercase n here, means that I'm like making this finite n, and when I remove that, means that I'm letting this go to infinity. So this acts on R by taking any sigma here, and xij will get mapped to xi sigma of j. So only on this in the second index, since the first one is kind of has only 2 options, 1 and 2, and the other one is varying. And with this convention, we have that the ideal I is just generated by S infinity of x11, x22 minus x12, x21. Or I can even write it as S infinity of I2, where I2 is just the first 2 by 2, the ideal of the first 2 by 2 minors. So when I only consider this part. So what this is saying is that in order to know that ideal, I just need to know this smaller part. Okay. Okay, then. Okay, so maybe to work out outside of this hour. So maybe question. Or problem. So generalize the example above to, let's say, 2 by 2 minors of the x c times n matrix. And so the question is, what is the smallest k such that our ideal in this case is S infinity of ik. Okay, so while so the question that was mentioned in fact before, it's a good question, because it sends us to a kind of a fundamental notion in this area called the filtration. So definition. Okay, so we have that, so a family I, n, n in n, where each in lives in this polynomial ring Rn, is S infinity filtration. If for n less or equal to m, we have the followings. 1, we have that in is included in im, so we have inclusion of m. 2, we have that Sn, when we apply it to In, gives us In again. And 3, Sm, when applied to In, still lives in Im. Okay, so if we compare this with the example we had earlier with the 2 by 2 minors, so if we call here In for us is like all the 2 by 2 minors of 2 by n lowercase n matrix. So if we take m greater than n, then like all the 2 by 2 minors of In live in are 2 by 2 minors of the Im. And so the first one is true. The second one, so applying Sn means just doing permutations on the columns. So if you do permutations on the columns, you still end up with minors in In. And if you do permutations now, you take In and you maybe permute with like larger m. The point is you will land in still minors that are not, most likely are not in Im, but they are in Im. So, and this is called S-infinity filtration. Now, I wrote this definition in terms of S-infinity, but it can be written like for any action that we apply on our algebraic object.
So in your
Yes.
that problem you propose, only first two columns are enough to generate the whole idea, right?
Could you repeat? I could not hear.
So the problem you proposed, so the value of k will be 2. So the
Yeah.
only two columns are enough to generate the whole idea.
Yes. Maybe, yeah, if you can also, you want another problem for that is you can go to n by n, like increase, yeah, but yes, your answer is correct. Okay.
Because the action is just shifting the rows and shifting the columns.
Yes. Yes. Okay. So now, let's, yeah, so, okay, so maybe, yeah, another problem. Oh, this was pink. Another problem is, so let's, you take this matrix X to be C times D times N. Okay, so this now has a picture of a tensor. It's not a 2 by 2, it's a order 3 kind of matrix. And again, consider the ideal of all 2 by 2 minors, so all directions here to make sure. And so the same question here, give a finite generating set up to S infinity. Okay. Now, so okay. So the theorem here is the following. We go to our main result. And this is a theorem. So I'm gonna, there is a version of this found by Hiller and Sullivan in the 2012 and by Nagel and Romer in 15, which says that, so let R be, where are we? Yes. So let's R be this polynomial ring R X C times N. Then any sim invariant ideal in R has a finite generating set up to
So
S
in the problem you proposed, so how the action is defined?
yeah, that's I left it as a you will tell me.
Okay.
Okay, so in this theorem, so the point is when we are in the setting where the polynomial ring is of this form, then every sim invariant ideal that lives here has a finite generating set always up to S infinity. In fact, the theorem is more general, but I'm putting it in the I'm trying to remove things that I think may as an introductory course may confuse us. I think this is a nice statement. I think that is enough for us. But yeah, so so this guarantees every time we have an ideal that lives in this polynomial ring that is invariant under the S infinity, then must have a finite generating set up to this group action. And now something, so you have been learning a lot about toric ideals and toric varieties by Thomas Kalle there. So in fact, many examples I'll mention here end up being in that setting, and all the examples I mentioned earlier end up being in that setting. So observation. So we have so all the above are toric ideals. So if we take so what should I call it? Okay, let me take phi will be from R x c times n, and this goes to R of y n z n such that xij is mapped to yi times zj. So the kernel, I claim here that the kernel of phi is exactly the ideal generated by 2 minors of x c times n. Okay, so this is a monomial map. So by definition, the kernel, by one of the definitions, the kernel is automatically a toric ideal. Okay. And maybe I'm gonna put again here why. So why is this true? Yeah, so yeah, where are we? Oh yeah, so we are here. And another problem that I find it, I do like this problem, so I'm gonna state it now, and you can look, you can try to figure it out. So let's yeah, so fix some n0 in n and consider the ideal generated by the S infinity orbits of polynomials x1 to the n plus xn to the n for n greater or equal to n0. And the question is how many elements are needed to generate the ideal. So it looks like there are infinitely many, because for any n we have a generator, but the answer is very nice, in fact. So I'm gonna let you think a little bit about that, then next time we can, I'll give the answer to that. Okay, so now we did mention things about this polynomial ring R of x c times n, which is, so this one is very friendly, or very nice, friendly, yeah. Now, what about, let's say, R of x, let's say n times n, or like this. So unfortunately, or the situation is more kind of nuanced when we leave this setting. There are good news and there are not so good news, but let's start with the good news. Let's start with a nice example. So let's consider now. So let's define with R and M to be the polynomial ring with variables x n times m, and let R be like the x n times n, and so let I and m to be the 2 by 2 minors of x n times m. Okay, so similar to before, but now, and let I itself to be the 2 by 2 minors of x n times n. So now we have our matrix x n times n, like x1 1, x2 1, and continues this way. Okay, so it has both directions go to infinity. And so now what we can do is, one alternative way is we define, so we take s n times s m, and this acts on R and M, such that if we take a sigma and we take a tau, and this will act on like xij as x, and sigma acts on I, and tau acts on j. Okay, so kind of now the first Sn is in charge of permuting the rows, and Sm is in charge of permuting the columns. And so with this, and similarly, we have S infinity times S infinity acting on R the same way. Okay, sigma tau xij x sigma phi of j. And then, so with this convention, we have that our ideal I is generated by S infinity times S infinity of just, again, the first minor. Okay, or we can write it also as infinity squared of I2. Okay, so all this is good. And now, where do things break? So I'm going to give the example. This example is called also no three-way interaction model. And later I'm going to explain why this name. So the idea is we take, so consider so we take phi from R of x n times n, and this is mapped to, I wrote them too big, this one. I will not have space. Okay, so P R of x n to the third, okay, means n by n by n, which goes to R of y n square z n square w n square, such that x I j k, because there are three indices, is mapped to y I j times z j k times w I k. Okay, so we take any choice of any two indices, and that gives us all these ij, jk, and ik. And I claim the kernel of phi is not finitely, or is not finite up to s infinity to the third. Okay, and this was proven first by Diaconis and Sturmfels in 1998. They proved, in fact, a more special version of this, not when everything goes to infinity, but when one of these kind of numbers, like we don't have n to the third, they proved it, in fact, for the version when we have r x 2 times n times n. When you restrict to these variables, they show that this is not finitely generated, because the ideal requires, so the answer is the y. So I'm going to give a hint of y. So y, the ideal kernel of phi requires generators of large, of like any degree for the first case, any degree. So if it requires generators of degree that just goes to infinity, then there is no way that a finite set of of polynomials can give us everything, because the group action preserves the degree. So like a polynomial of degree, let's say 100, cannot, up to, like, by applying symmetry, cannot give us a polynomial of degree 101. So
Aida, excuse me. When you are discussing these maps, so you are not taking care of the grading?
no, no.
No, okay.
No, I'm also thinking standard grading right now, every
Okay.
time. Yes.
Okay.
Okay, so then, yeah, so I will share some. So I would love for the participants that are interested to try out examples on Macaulay 2. I will share some code on Macaulay 2 already, like to kind of as a starting point. And if you have not used Macaulay 2 in the past, you can, like, there is an online version that you can use, and you can also check yourself for, like, you cannot work with infinity directly, but you can check that for, like, if you take some fixed values here, not infinity values, some fixed values, what is the ideal? If you increase these values, what is the ideal? And you will see that the new ideal that you get with, like, larger indices will require more and more, will require generators of degree higher and higher every time. So that means that there is no way you can have a stabilization phenomena happening. Okay. Any questions?
So far, so good.
Okay. So, in fact, for the case when that Diaconis and Sturmfeld proved in this setting, when we have 2 n by n, the generators look extremely nice. But otherwise, the Loera and On, they proved that in a more general setting, the generators can be sufficiently complicated. So it's a mess. That's all. Like there is not even a pattern kind of that could help represent them. Okay, so and then I will. Oh yeah, so maybe I'll say this is part of lecture 2. I called it lecture 2 because it has a different name, but yeah. 2. Okay, so this is on independent. Then that here. Okay, and so this is mainly based on the paper by Hiller and Sullivan. And from the one that I mentioned, 2012. And but before I go there, we'll need some notation and all that. Okay, so the idea is that how do we manage outside that nice polynomial ring that we said, like outside, where are we? Yeah. So when we are not here, what do we do? So there is hope, and that's what we will see. Okay, so for this, so the motivation comes from hierarchical models, ideals of hierarchical models. In statistics. Okay, so for that we will need some notation. So let's let delta be a simplicial complex or like a hypergraph. So for instance, one example would be one, 3, 4. So this is a simplicial complex. So if you have not seen this before, so it's like a visualization that can be given by points, lines, segments, triangles, generalizations of these triangles, which are called, all of these are called simplices, and combinations of them. And it says that if you have a simplex there, so simplex are kind of these kind of things, either a point, a line segment, built-in triangle, or tetrahedron, like a generalization of that. So convex hull of like a bunch of points. And the definition of a simplicial complex requires that for any simplex you have, each face of that simplex, so each subset, must be also included in the definition of simplicial complexes, and the intersection of any two of them should be also an element in the simplicial complex. So maybe, yeah, if you have not seen it, maybe I'll recommend to look at the word, but visualization right now it's something like this. So we have a simplicial complex. Okay, so as I said, these are called simplices, and also for our settings, also faces. And then facets are maximal faces. So for instance, in our case, facet of our delta here is going to be the set 1 to 4 2, 3, and 3, 4. Okay. And now, so we take delta. So maybe let's say delta on n. So on n vertices. So 1 through n. So here n is equal to 4. Okay, so let R be R1. Oh, maybe I should. Honestly, I'm sorry. I'm going to call this M just because we have used N for other things. Okay, so R1 through Rm. And so this one be in like Z greater than 0 to the M. And then, so positive integers. For simplicity, I'm going to call this R like this. If R is a vector, this will be R1 times and so on times is this Cartesian product. Okay, and I will also denote with R, F will be the product of Ri, where I lives in F, where F is a subset in of M. Okay, so it's kind of the projection onto the subset F. Okay, so now to define these hierarchical models, we will have this R. With R, we'll denote the polynomial ring X R. So means like R1 times R2 and so on. And we will also have S R delta will be the polynomial ring with variables. We will call them Y, F, and here we will call R, F. And with this information, we denote phi of R delta will be the map from R to S R delta such that X I1 through IM will get mapped to now the product of Y F or F in the facet of delta. And here will be IF. So it's a projection of this I onto the indices F. So maybe if it looks kind of heavy as a definition, let's look at that one example. So let's take this simplicial complex here, 1, 2, 3. So the facet of this delta are 1, 2, and 2, 3. And then, yes, and let's take R here to be, let's say, 2, 3, 2. And then we take the map. Our map will be from, so yeah, we have R to the, yeah, so we have from R of x111 till to x232 that gets mapped to R of, I'm gonna, just for simplicity, I'm gonna call this y11, y23, and then we will have z11, z32. Kind of, this is for like y12, and this is for y23, kind of the set. For simplicity, I'm calling them Z. Okay, such that X, I, J, K gets mapped. So according to that, it says for every facet. So we have two facets, 1, 2, and 2, 3. So we take the first facet, we have this Y for that facet, and then we project down I, J, K to the what the first facet is saying, 1, 2, to the first index and the second index. So will be I, J times. We take Y for the second one, and we project to what the second facet is saying. So the second and the third, so it's JK. Is this clear?
Maybe
ZJK, maybe.
Sorry?
It's ZJK.
Oh, yes, thank you. Yes, I did. Yeah, thank you. Yes, it's ZJK. Yes. Okay. Do we want to, yeah, so maybe as a kind of in the break, we have a break soon. So during the break, maybe one can try.
Yeah.
So write down the map for what's the name? It's gonna be for I'm gonna call it figure 1. Figure 1 is this one here. Okay, so write down the map for this one. And so we can see if we understood the definition or not. Also, by the way, when is the break? So I don't wanna.
No, it's break time now.
Okay.
I guess we started a bit late, so that's why
Okay, yeah, no, all good. So just wanted to make sure. Yeah, so then this is a good place that people can try this out, and then we will we'll see what we'll do with this.
Yeah. It's 30 minutes break. Let's gather once again at 4 so that Aida can continue with more examples as a tutorial.
Okay.
Have some coffee, Aida. Okay, have some coffee, participants.